This is the Science Fair Digital Computer Kit. It was sold in the US by Radio Shack Corporation and was announced in their 1978 catalogue. As you can see here, it would have retailed for $24.95. Although it was announced in the 78 catalogue, as you can see here, it was actually available from the 30th of September 1977. As it happens, 77 was the same year that Radio Shack announced and released its TRS-80 computer, and so this definitely represents two different ends of the computing spectrum. Although the box for my unit is a little worse for the wear, as you can see it contains 100 safe and exciting experiments. And if we look along the front of the unit, we can see this particular one was manufactured in Japan for Radio Shack, a division of Tandy Corp. If we look inside the box, we can see what's included. Inside, we see the Digital Computer Kit user manual, and this is a nicely illustrated manual with details of the various programs you can provide with the unit, and we'll look at that more closely in just a moment. We also see a few bags of wires, and these allow us to wire different programs together. Slipped down the back here, we have some programming cards, and these represent the indicators that we can see on this part of the display, and they simply slide in. We'll see some of that in a moment. And finally, we have the unit itself. If we go ahead and turn the unit over, we can see behind here I have simply tucked the box that the bulbs would have come in, just here. And so that's just tucked out of the way. But we have a date code sticker here. And so this indicates that this particular unit was manufactured in the 8th month of a year ending in 7. So the Digital Computer Kit was available from 1977 till approximately 1985, and so we can discern that this is probably an original unit from one of the very early production runs. If we take a look inside the user manual, we can learn more about the Digital Computer Kit. And this is a very nice manual. It's in black and white predominantly, although it does have some colour text in red. It has a list of experiments and some history about computing, including some illustrations of various computers that were available at the time. We can see how the computer empowers users and some history of computation, including the abacus, the Pascal calculator, the Leibniz calculator, Napier bones, punch cards from Joseph Jacquard, and the Analytical Engine, or Difference Engine, by Charles Babbage. We also progress through to Hermann Hollerith and his tabulating machines, as well as more recent developments in digital computing, and an illustration of the ENIAC. The manual goes on to describe the arithmetic used by electronic computers, including binary, and details some information about core memory, which would have been contemporary with some of the machines. There's some other details about using computers and how they work, including details on how programs are designed and stored in machines, as well as some of the careers that might be available to computer users, including design engineers, production foremen, programmers, and even key punch operators for those punched cards. The manual then goes on to explain how to assemble the computer, and so it's interesting that this particular unit came disassembled with the exception of a single unit of switches here, and I'll show you one of those more closely later in the video. Once we've built and tested the unit, the manual continues with programming. And as you can see here, the very first program in this manual is called Crossing the River, and it uses program card number 1, which you can see has been slid into the unit through the window here. Beneath the slide-in piece of plastic, and these slips are indeed plastic, we can see various bulbs here. In fact, there are 10 in total, and these can be illuminated by the circuits we create. Let me just slide this back in. The first program is a representation of the classic river crossing problem, in this case represented by a farmer, a wolf, a goat, and a cabbage. These are on one side of the riverbank, and they need to be on the other. There is a small boat available on the river, but only 2 items can go across at the same time. It's important to note if you leave certain items together, then one or the other may become damaged. For example, if you leave the wolf with the goat, it may get hungry and eat the goat, and likewise, if you leave the goat with the cabbage may eat the cabbage. So it's important to get everything across without losing any of the items. Only the farmer can steer and row the boat. Now, the diagram here shows you how you need to wire up the circuits, and as you can see, I've gone ahead and wired that up on the device. So let's give it a go and see how it might work. If we go ahead and pull all these switches towards us to make sure all of them are off, we can begin the program. We do so by pressing the switch here, and when we do so, we can see all of our items are now on the left-hand side. We have the farmer, the wolf, the goat, and the cabbage. And neither of our danger lights are currently illuminated. If I was to go ahead and move the farmer and the wolf to the other side of the river by pushing these switches upwards and pressing this switch on the right-hand side, we can see we now have the farmer and the wolf on the right side of the bank. They have now travelled across by the boat, but this leaves us with danger on the left bank. This is because the goat will eat the cabbage, so obviously that's not going to work. If instead we have the farmer try and protect the cabbage, we can see that these are now moved over to the right-hand side, but we still have danger on the left bank because the wolf will now eat the goat. Of course, that tells us that the only logical move to make at this point is to move the farmer and the goat across the river, like so, and you can see we have the wolf and the cabbage on the left, the farmer and the goat on the right, and no danger on either of the banks. We can proceed by moving the farmer back to the left bank and leaving the goat where it is. And again, no danger. And now this time the farmer can take one of the other items across on the boat. For example, let's take the wolf. And now we've left the cabbage on its own. Now the farmer needs to go back to get the cabbage, but of course it can't leave the wolf with the goat. So what it's going to do is it's now going to need to take the goat with it across the river. We do that by moving these switches down. And now the wolf's on its own on the right bank, and the farmer is with the goat and the cabbage, keeping them safely apart. That means we're now safe to move the farmer and the cabbage to the right-hand side. Still no danger. And now the farmer can go back to get the goat, and the wolf will hopefully leave the cabbage alone. Let's check that out. And we still have no problems. The farmer is now with the goat, and the wolf is leaving the cabbage. At this point, we can take both of the farmer and the goat across the river, and this should complete our problem. And there we go. No danger, and all items on the right side of the riverbank. So now we've managed to solve this particular riddle. How does this computer actually work? Well, what I can do here is lift the unit up slightly and pop out one of these sliding units. So this one here actually isn't currently used. The wires on top of it are just laid in place. So if I gently pop that out, we can see what the construction of these units actually looks like inside. So here is one of the sliding switches we've just been operating, and as you can see, you can move it up and down. And what I'm going to do is dismantle it as it would have come when you purchased the unit originally. So I'm going to take off these control knobs and then gently pop out this piece here. Okay, so now we've more or less separated this here. You can see the construction of these sliders, and in fact, they are nothing but springs. So by using just wires and springs, we're able to construct switches that can do computation. And I think that's kind of neat and interesting. So let me reassemble this just by popping these bits back together. And as you can see, as you slide this backwards and forwards, these springs make contact between either the bottom or upper pair of contacts, and this forms the switches. If you slide upwards, these two top connections are connected in each group of 4, and if you slide downwards, these bottom 2 connections here are connected. And so this allows us to have an on and off state for each switch with actual electrical connection between both in either of those states. Let me pop on the small pieces here, and I can reinstall this switch back in the main unit. If we revisit the user manual for the digital computer kit, although the introduction is quite comprehensive in detailing the history of computing, the details around how individual programs work is less so. While the diagrams that illustrate how to connect these wires are very reasonable and allow you to implement each of the programs, there's not a lot of detail about how they actually work. And in fact, although there are 100 programs in this book, none of them really explain what you need to do if you'd like to go ahead and write your own. Of course, a little thing like that not being featured in the manual isn't going to stop us. So I've gone ahead and printed out some blank programming sheets that I can write my own programs on, and I've created these slide-in pieces of paper that I can use instead of the plastic to provide windows that I can also write on as well. So let's disassemble this program and move on to a new one. Now the computer is entirely deprogrammed, and pressing this button will have no effect on the lights. In a previous video, I showed you a recreation of the Digicomp 1, a mechanical binary computer. In that demonstration, we saw a binary counting program. And so what I thought would be fun is to recreate a binary counting program on this electromechanical binary computer we have in front of us today. To do so, I've gone ahead and represented what we would expect to see from the inputs and outputs of a binary counter. As you can see here, for an input of 0, we expect an output of 1. For an input of 1, an output of 2. For an input of 2, an output of 3. And for an input of 3, an output of 4. To make this a binary counter, I've gone ahead and translated this into binary here. And we can represent that on the lamps that are installed in our device here. Each lamp can only represent a single binary digit, and so I've broken these into two separate columns. We have the input column here and an input column here, and I've labelled these lowercase a and lowercase b as two separate binary digits. Equally on the output, I've created an output A, an output B, and an output C. To differentiate them, I've used capital letters here versus the lowercase here. And again, each of these represents an individual column that we can see in the binary translation just above. So let's go ahead and see if we can wire up an input so we can understand how we can connect up our device. I've gone ahead and filled in one of my programming cards for the unit here, and this is handling just the inputs. And I've decided that I'm going to have my input A on this switch here and input B on this switch here. What I want to do is show what the input values are, and so I've wired up a very simple circuit here that just allows us to illuminate the bulbs above these switches on those inputs. You can see here I've labelled this as 2 to the 0, and 2 to the 0 is a 1, so this is the 1s column. And here this is labelled as 2 to the 1, which is 2, and so that is the 2s column. And so these are the A and B columns that we saw on our programming sheet. I've gone ahead and filled in one of my programming sheet labels here to go into the display, as you can see here with the same notation, although I've added the lowercase a and b and the uppercase A, B and C here for clarity. So let's go ahead and slide this in. In this case, I've made these of paper, and so they will be slightly dimmer than we saw with the previous plastic units. So what am I doing in this program? Well, the first thing I want to do is connect via the switch, and so I have a wire going from the common point to the switch, and then I'm taking the electricity here all the way over to the first connection point on this switch here. Now what happens is, when we push this switch up, these two upper terminals, and in fact all of the upper terminals on each of these groups of 4, become connected. And so if I want to illuminate the bulb, I can simply add a wire from this output terminal up to the bulb. Now because I have two switches, I've gone ahead and connected the power across, just made a jumper wire here, and again connected that up like so. So let's wire this circuit up and see how we get on. So before we power up the computer by pressing this switch here, what I'm going to do is pull all of these into the lower position, so they're all actually turned off, all the way along the unit like so. Now when I press the switch, I expect absolutely nothing to happen because my two input switches here are off. But here now, if I turn on this first switch, I would expect to see this bulb illuminate. So let's see if that happens. And there we go. Because I have this input switch here, input A on, I can see a 1 on the output. And of course, that maps with what we expected here. When I had no switches turned on, I got a 0 output, neither of the bulbs illuminated, but when I had the first switch on, I got this 1 here. So this is representing the input. Of course, I can go through and represent the other two values, the 2 and the 3, with the switches by swapping them like so. And if we press the button, the left-hand light illuminates. And if I put both of these on, we see 3 on the input value. So now the question remains, how do we get these input values to translate to output values on the right-hand side here? Well, again, let's go back to our binary counter description here. And underneath this slip of paper, I've got some details about how we can compute the output values. What I've done here is looked at the output values we expect, and wherever there is a light in each column, a 1 indicated here, I've gone ahead and put the required equation for Boolean logic. Now, why don't I bother with anything with a 0? Well, of course, as we saw a moment ago, if I simply turn on the power with none of the switches up, the bulbs are off by default, and so I don't need to provide anything to illuminate those lamps. Looking at this sheet here, we can see the various options, and so I need to have this light here, A, illuminate, when I have a situation where B is 0 or false, and A is 0 or false. And so I need to turn these falses or offs into ons. And so I say when we have a not B and that's what this symbol here means, and not A, we end up with a 1 or an illumination of the lamp. If we look down the column further, we see the next time we see an illumination of that lamp is just here. And so we can see that happens when we have B being illuminated and nothing on A. And so we say that's where we have B and not, or the inverse of A. And so that will give us a 1 in this column as well. So that's great. We have similar logic going on for the B column, and I've only filled these in for places where we have illumination. And again, for the C column with this quite simple equation that goes on here. In this case, C is only illuminated when both B and A are true. And so we have B and A. So actually, there's quite a lot of switches to wire up here to make all of this happen. But it turns out we can actually simplify this logic somewhat. In 1937, a fellow by the name of Claude E. Shannon was working on his master's thesis, and he later published this in 1938 as a symbolic analysis of relay and switching circuits. What Shannon was really thinking about when he was working on this paper was the idea of telephone exchanges, which at the time were made up of switches and wires that we would connect together. And he wanted to do so in the most efficient form so that we could achieve the desired circuit outcome. That is to say, connect the appropriate users together at the end of a telephone exchange. As it happens, the problem here is very similar to the one we are trying to solve today with our digital computer. We have a variety of switches and wires we can use to connect them together, and it'd be nice to do so in the most efficient fashion so that we can illuminate our lamps and display the correct value on these output displays. In the paper, Shannon shows us how to convert from Boolean logic and binary notation into something that we can represent simply with these switches. He does so using a variety of theorems and postulates that he puts forward about how we should represent that logic, and he simplifies that with some algebra that looks fairly scary here. However, we can think about it quite simply as shown in this particular pair of diagrams. First, we have a fairly complicated switch arrangement that we'd like to simplify. So we convert it into its algebraic representation, we simplify that algebra, and then we end up converting it back to a switch representation. As Shannon shows here, both of these switch networks work in the exact same way and have the exact same output, but this one uses far fewer switches. Shannon shows in his work that it's possible to distill down any complex pattern into a situation where we only have 2 representations of every single switch, one in the on position, which is represented by the letter itself, and one in the off position, which is represented by the letter and this apostrophe or not or prime symbol. This represents the inverse of the default state for that switch. Again, as it happens, this works very well with our digital computer here. We have these switches that we can push into the up position, and that connects these contacts across the top here. And in each of these columns here, each of these groups of 4, the top 2 contacts will now be connected. When I pull the switch downwards, that instead connects the bottom positions. And of course, a switch can only be in one of those 2 positions, and that's true in Shannon's paper as well. So this is going to work really well for converting our logic into something we can represent on these switches. Shannon comes up with a few basic things we need to know about how we do this algebra in his paper. And the one that really confused me the very first time I read this paper was how he represents the switches themselves. What's important here is he represents a closed circuit with a 0. We're used to a binary 1, meaning the light will be illuminated. But in Shannon's case, a 0 means the circuit is closed or the lamp is on. The reason for this is twofold. First, it means that we have a representation that Shannon calls impedances. Only where the circuit can be impeded or switched off do we need a 1. So these 1s really represent switches we need in the network. Where we don't need a switch, we can simply replace it with a 0, and in our circuit design, replace it with a wire. The other reason is it allows much simpler combinations using the algebra we'll see later as we distill down our circuits. So let's go ahead and look at what we've come up with so far. The first thing we need to do is to convert our existing binary notation and logical analysis into something compatible with Shannon's theorems. As you can see here, I have my input and output columns just from before. To convert them to Shannon's notation, I need to replace everything where the switches are closed with a 0 and everything where the switches are open with a 1. And so that just requires us to invert every single bit in our input and output columns here. So you can see here, every 0 becomes a 1 and every 1 becomes a 0. And that's true for both the output and the input sides. I've also converted our logical notations here into a format compatible with Shannon's. Just like before, I only need to have some logic here when the circuit is going to be closed. Of course, by default, when the circuits are all open, none of the bulbs illuminate. So I don't need to worry about any of those situations. In this case, I now need to have some logic where we have a 0, and so these are actually in the same position they were before. It's only the exact representation that's changed. Because of this revised notation, we now, instead of using the AND symbol, we actually use a plus sign to represent the AND. We can see this most clearly in the C column here. The only scenario where we have a illumination in the C column is in this particular position here. In this situation, we need both B and A to be closed. So when both of these situations are closed, both of these switches are down, and we have the lamp illuminate. Of course, recalling that these zeros here mean the circuits are closed, or the switches are in the down position. We can clearly do this maths now here, and we can see 0 plus 0 will equal a 0. And so a closed circuit for B and a closed circuit for A will equal a closed circuit which illuminates the lamp. For our A and B outputs here, we actually have options that we can pick from, depending on the particular pattern that we have on the input side. To represent these ORs, we use a multiplication symbol, and this is represented here as an example. In this circuit, we can have B depressed or A depressed, and so if either B or A is 0, the lamp illuminates. We can imagine if B is 0 but A is 1, so A is open, a break in the circuit, this particular piece B would be closed and the lamp would illuminate. That would be 0 times 1 would equal 0, and so the lamp illuminates. The overall circuit is a 0. Similarly, if A was 0, so this is a closed circuit, but B was 1, a broken circuit, we would have 1 times 0, which would equal 0, which would mean the entire circuit would be closed and the lamp would illuminate. This is the advantage of this particular approach that Shannon has taken. So let's see how we can apply the simplifications that Shannon proposes to this A output just here. So here I've taken the two input equations available to illuminate the bit for A. We can either have not B plus not A, or B plus not A. And this is representing by the multiplication for the two alternate paths, and again the addition representing the series circuits. So how do we go about simplifying these expressions? Well, first we need to multiply these two out. And we can see here that when we do so, we get not B times B, plus not B times not A, plus not A times B, plus not A times not A. I put a little cheat sheet to remind us of some basic expressions up in the top right hand side here. What this shows us is that anything times itself results in itself. So a 0 times a 0 is a 0, and a 1 times a 1 is a 1. If you look closely here, you see we have not a times not a. Now we can simplify this no matter what the value of that is, it can be a 0 or a 1, down to just itself. Because if it's a 0, they'll both be zeros. So 0 times 0 would be 0. And if it's a 1, well, both of them would be 1s. So 1 times a 1 is a 1. So we don't need this multiplication here, and we can simplify it down to a single switch contact as so. On the other end of the expression just here, we can see we have b times not b. And again, we have a cheat sheet here to remind us of some basic maths, in that a 0 times a 1 is the same as a 1 times a 0, and overall that will result in a 0. So what we're saying here is no matter what the value of b, if it's a 1 or a 0, the not b will be the opposite. And so no matter which values they have, overall they will turn out to be a 0. So if not b is a 1 and b is a 0, we can see this expression here, 1 times 0 is 0. And if not b is a 0 and b is a 1, well, we have 0 times 1 still equals 0. So we can actually remove this expression and replace it with a simple 0. Now remember, in Shannon's notations, these represent the required switches. And when we have a 0, we don't require a switch, and we can replace it with a wire. So what we're saying here is that the not b times b can actually be removed entirely. This leaves us with this actually fairly complicated expression, which I've converted back into switches that we can see here. This is saying we have not b or not a, represented by these parallel circuits of not b and not a. And they are connected in series to not a or b, so not a or b, so either of those could be true and the circuit would continue, and a series connection here finally to a not a. Now if we think about this carefully, we can see that for the lamp to ever illuminate, not a must take the value of 0. Now I'm not saying that not a is always 0, I'm saying that for the overall circuit to illuminate the bulb, it must be 0. That means it's safe to assume in all other places in the equation, except this switch here, that not a is 0, because for the lamp to illuminate, it must be true. So we can go ahead and replace in our expression here all of the not a's with zeros. And so in this case, we have not b times not a, and we convert that to not b times 0, plus not a times b, which we convert to 0 times b, plus not a. So we still need this final not a to be an unknown value, but for the other ones, we've managed to eradicate them from the expression. Now, just as before, anything times 0 will be 0, and so that means we can go ahead and eliminate those not b's and b's from our expression. And that means we can simplify our overall equation down to simply not a. And so that means that if the switch is in the off position, the lamp should illuminate. So now we've figured out the required circuit for output A, let's take a closer look at output B. So again, I've represented our derived logic as a circuit of switches. The first step again is to multiply out those values here. And this time we have not b times b, plus not b times not a, plus a times b, plus a times not a. And again, we can do some simplifications that we saw before. Not b times b is a case where we can have 0 times 1 or 1 times 0 to be 0. So no matter the values here, that can be boiled down to a 0, and we've done that here. And the same is true for a times not a. No matter the value of a, if it's 1 or 0, not a must be the inverse. And so this truism applies here, and we end up with a 0. So both of these ends of the equation, again, go away. That leaves us with not b times not a plus a times b. And we can see a switch representation of that here. Now, unfortunately, we can't simplify this any further. We can't say that either a or b is true or false. And that's because they only exist in these parallel circuits, and those individual combinations of parallel circuits only exist once. These two circuits are actually equivalent, but neither of them is simpler than the other. There are 4 switch requirements in both combinations. What we can do, though, is look at the circuits in a different way using De Morgan's theorem. Shannon explains De Morgan's theorem very simply by saying that the negative of any function may be obtained by replacing each variable by its negative and interchanging the plus and multiplication symbols. He further goes on to explain that explicit and implicit parentheses will of course remain in the same places, and provides an example. So let's have a look at how that would apply to our circuit. Here I've taken our final expression and inverted it, and using De Morgan's theorem I've gone ahead and converted all of the multiplications to plus signs and all of the plus signs to multiplications. As you can see, I preserved the implicit parentheses of the multiplication as shown here, so that what was a multiplication is now an addition, but that addition still happens first. This allows me to multiply this out and apply the same simplifications we've been using previously. And again, we can see, for example, here that b times not b can be simplified down to a 0 because of this expression just up here. 0 times 1 or 1 times 0 remains 0. Likewise for a times not a becomes a 0 as well. We then end up with this expression here, which again has the same number of combinations of switch contacts in that we had before. At this point, we must remember that before applying De Morgan's theorem, we inverted our logic. So this expression here represents precisely the inverse of what we actually need in our circuit design. To get back to something we can actually use, we need to invert our expression again. And we can see that I've done that just here. I've made one minor refinement of that expression just at the end, and you can see I've replaced not a plus b with b plus not a. Now, these are entirely equivalent. Either these values are exactly the same, and so they represent either 1 plus 1 or 0 plus 0, or they're the opposite of each other, in which case that's the same as 0 plus 1, which of course is the same as 1 plus 0. The order of these additions doesn't actually matter as long as they're in the parentheses. Now, the reason I've done that is if you look closely here, you can see we've actually arrived back at the original circuit design we had when we started. So although we weren't able to simplify the circuit, we've demonstrated using De Morgan's theorem and Shannon's notation that these circuits are entirely equivalent. So let's go ahead and see how we can represent them on a wiring diagram. So let's look at output A. I've reserved this first row of contacts for the input values, and so these illuminate the input lamps. So let's do our output A on this second row of contacts. If we look back at the values that Shannon helped us derive, we can see that in the final expression, output A is represented by not the input A. And so in this particular representation, that means when the switches are in the down position, we want a connection which is going to illuminate the lamp. In our digital computer, that means when we pull the switches down, this will connect all of the lower contacts in each of these groups. And so if I'm using this row here, I need to make sure I have electricity into a lower contact just here. And so I already have some electricity coming in here to provide our outputs. So I'm just going to tap off of that here and provide that into the NOT switch here. And the output of that needs to connect up to the lamp, and we can flow that wire here, and that is to our A output. Now let's move on to the B output here. Again, I'm going to reserve a new row of contacts for this particular output. It is possible to reuse the existing switches and contacts we already have, but for understandability and cleanliness in this design, I've separated them out into their own rows across the switches. We can refer to our diagrams here and remember that both of these circuits are entirely equivalent. So we could actually use either. And in fact, if you go ahead and inspect what I've done, I think you'll be able to find both. But I'm going to explain it in the context of this circuit just here. So the first thing I've gone ahead and done is for the A input here, I've gone ahead and decided to use the A or B. And so again, I need to go ahead and grab some electricity. And so this is an always connected terminal just here. And so I've connected it on just as follows. I've gone ahead and then said that if A is connected, so that would be through here, or by creating a parallel circuit, B is connected. And so I've gone ahead and tapped the electricity from that over to here as well. By putting these in parallel, that means that this E output terminal here will always have power on it if one of these switches are on, which is what we require in this design here. We also need to have a connection via this connection here, and we need to say when not B or not A. So again, because we know that if this part of the circuit is now true, our E terminals here will have power on, and they're connected, so both of them will, we can tap off of that to create the connection here. So we're tapping between the two, and we are tapping down to see on the not A switch first. And so I've gone not A here, And I've gone ahead and said, or we can have not be, and that's why this is a loop all the way through as well. Now, again, I've connected both of these Fs together, and so that represents the connection here. And so now I can tap off of the F output and off to the connection. And so in this instance, I've actually gone ahead and put the bulb on the other side of the circuit, but of course it doesn't matter which side it's on in this particular instance. So we can go ahead and we can tap that through to here for the B output. Finally, we have the C output, and if you remember from our original diagram here, the C output is particularly simple. It is just B plus A, and that's actually represented by this example series circuit here, so I didn't need to do a separate derivation. And we can look at what I've done here, and that's in green for this pre-existing circuit. And what I've gone ahead and done is I've tapped off the always on electricity supply from this wire here, and I've said if A, this column here, and B is connected, then I can go ahead and illuminate this lamp here. And so that represents this switching circuit here. And again, my bulb's on the other side, but it doesn't matter which end it's on. So what I'm going to do now is wire up this diagram on the digital computer and see if it actually works. So let's go ahead and see if I made any mistakes. First, we want to make sure that these three switches are certainly all off. And when we go ahead and press this switch here, we should expect to see a 1 illuminate on the output. And there we go, we have our number 1. And that's exactly what we'd expect from our sheet here. An input of 0 results in an output of 1. Let's switch to a binary 1 by pushing this switch up and then pressing the switch again, and we should see a 2. And our input of 1 equals an output of 2. And again, that's exactly what we see on our output sheet here. Now let's try an input of 2. And we see an output of 3. Input of 2 and an output of 3. Finally, let's see an input of 3. And we should see an output of 4. And there we go. In my video about the Digicomp 1, I demonstrate a binary counter with 3 bits of digital input. So I thought it was only fair to go ahead and extend this design to allow a 3-bit input binary counter for the science fair digital computer. Let's go ahead and implement this and see how this circuit works. So as you can see, other than the additional input lamp, I only had to change the bottom 2 rows of contacts. So let's pick up where we left off and see how we get on. Before, for the input of 3, we had an output of 4. Let's see if that still works. An input of 3 and an output of 4. Let's try an input of 4. An input of 4 results in an output of 5. Input of 5, output of 6. Input of 6, output of 7. And an input of 7 gives us our output of 8. So using nothing but switches and wires, we've been able to encode basic binary logic. If instead of output lamps we'd connected up electrically actuated relays, we'd have the basics of a relay computer. And these are the same types of machines that evolved through vacuum tubes and valves into the modern transistorized devices we have today. So I hope you found this demonstration of the Science Fair Digital Computer Kit and Claude Shannon's inspirational work that laid the foundations for modern digital computers interesting, and I hope to speak to you again soon in the next one.